Welcome to the Cinematic Explainer, where we are diving headfirst into the fascinating, infinite universe of real numbers. Right off the bat, I want you to picture a glowing number line stretching endlessly in both directions. It's just going on and on forever. Every single tiny pinpoint on that infinite line represents a real number. Today, we're going to explore the actual mathematical physics of this space. We're talking uncovering the hidden logic, the beautiful patterns, and the underlying rules that literally govern Class 10 mathematics. It's going to be a fun ride, so let's get into it. So here's our master roadmap for today. We'll start with the mind-blowing discovery of irrationals, lay out the rules of the number line, talk about infinite density, dig into the prime DNA of math, decode some decimal expansions, and wrap it all up with the ultimate exam playbook. All right, let's kick things off with Section 1, the discovery of irrationals, or as I like to call it, the Greek anomaly. Okay, let's start with a historical shocker that, I kid you not, completely broke the ancient Greek understanding of the universe. The big question was, can every number be written as a simple fraction? Now, the Greeks, they firmly believed the answer to this was a resounding yes. They thought every single number in existence could be perfectly expressed as a clean, neat ratio of two integers. To them, the universe was tidy. It made perfect sense. But then, they stumbled upon the square root of 2. And this single number completely defied their logic and shattered their perfect rational world. You might be wondering, how exactly does it defy logic? Well, we use this awesome detective technique called proof by contradiction to show exactly why the square root of 2 is utterly irrational. Basically, we start by assuming the exact opposite. Let's pretend root 2 actually is a perfectly clean fraction p over q in its absolute lowest form. But as we step through the algebra and square both sides, we suddenly prove that p must be an even number. And if we substitute that back in, we prove q must also be an even number. Wait a minute. Actually, stop right there. If both p and q are even, they can obviously both be divided by 2, right? That completely contradicts our very first assumption that the fraction was in its lowest form. It's a literal mathematical trap. Root 2 simply cannot be a fraction. But here is the wild part. Even though it can't be written as a perfect fraction and its decimals just loop and go on forever without ever repeating, the square root of 2 still anchors itself to a fixed physical spot on our glowing number line, right around 1.414. It actually exists. And along with other crazy numbers like pi, root 3, and root 5, these irrational numbers claim their permanent space in reality. Moving right along to Section 2, rules of the number line. The mathematical physics of it all. So now that our number line officially includes these infinite, messy, irrational numbers, we've got to establish the fundamental laws of physics governing this space. One of the most interesting is the closure property. Think of this property as like an invisible boundary or a VIP club. It ensures that when you take any real numbers and add, subtract, multiply, or divide them, the result is safely trapped inside the universe of real numbers. So 5 plus 7 is 12. That's a real number. 10 divided by 2 is 5, real number. But look closely at division by 0. If you try to divide 5 by 0, the result is undefined. It completely breaks the rules of our mathematical physics. You simply cannot divide by 0. Now, alongside closure, we have these 3 golden rules. Honestly, these are the unbreakable physical laws that dictate exactly how numbers interact with one another. First up, the commutative property. This just tells us that order doesn't matter for addition or multiplication. 3 plus 7 is exactly the same as 7 plus 3. Easy, right? Then, the associative property proves that how we group our numbers doesn't change the final result. And finally, the distributive property shows how multiplication smoothly spreads out over addition. These 3 properties are absolutely critical tools you're going to use to manipulate equations. Okay, let's jump into Section 3, operations and infinite density. Time to start mixing the elements. We know the rules now, but what actually happens when we start mixing these elements together? Like, what happens when clean rational numbers and messy irrational numbers collide head-on the number line? Well, a rational plus a rational stays clean and rational, but if you add an irrational to a rational, like root 2 plus 3, the messiness totally takes over. The result is irrational. Add 2 irrationals, still irrational. But here is the crucial point, and honestly, it's a beautiful twist. Multiplying 2 messy irrational numbers together, like root 2 times root 2, can surprisingly snap right back into a perfect, clean, rational number. In this case, just 2. It's like chaos suddenly creating order out of nowhere. And all this crazy mixing, It happens in a space of infinite density. Imagine doing a cinematic zoom-in between any two numbers on our line, say between the integers 2 and 3. As you zoom, it reveals an infinite, glowing galaxy of decimals tucked right between them. You have 2.1, 2.2, 2.2567, and you can just keep zooming in forever. Between any two fractions, there are infinitely many more fractions. That, my friends, is the density property in action. Moving to Section 4, Primes and the Fundamental Theorem. We're looking at the actual DNA of numbers now. Let's transition from that infinite cosmic scale we were just looking at right down to the atomic scale of numbers. Because to truly understand numbers, you have to understand what they are built from. I want you to think of prime numbers like 2, 3, 5, and 7 as the fundamental raw atoms of our mathematical universe. They can only be divided by 1 and themselves. They have exactly 2 factors, period. On the other hand, we have composite numbers like 4, 6, and 8. These are basically the molecules built by smashing those basic prime atoms together. But hey, before we start building any molecules, it is highly crucial that you remember these two unique anomalies in the atomic structure of numbers. First, the number 2 is the absolute only even prime number in existence. No other even number is prime. Second, the number 1 sits in a weird class all of its own. It is neither prime nor composite. Seriously, lock those 2 facts in your memory right now for the exams. So let's see how these atoms actually build molecules by totally deconstructing the number 420 using an animated prime factorization tree. We start breaking it down. Okay, it's 2 times 210. Break that 210 down further and you get 2 times 105. Eventually, we hit the absolute rock bottom, the raw prime factors. 2 squared times 3 times 5 times 7. And this brilliantly illustrates the fundamental theorem of arithmetic. This theorem basically proves that every single composite number has a completely unique DNA sequence of primes. No other combination of primes in the entire universe will ever multiply together to give you 420. It is a one-of-a-kind fingerprint. Section 5. Decoding decimal expansions. Time to learn the predictor code. Now, what if I told you we could actually use this prime DNA as a literal cheat code? A way to predict the future behavior of a fraction without ever actually having to divide it out. Check this out. If you have a fraction in its lowest form, just look at the denominator, the bottom number, q. Break it down into its prime DNA. If those prime atoms are only 2s or 5s, boom, that decimal will cleanly stop. It's a terminating decimal. But if there's literally any other prime factor lurking in that denominator, a 3, a 7, an 11, then that decimal is going to loop endlessly. It becomes a non-terminating recurring decimal. Just by looking exclusively at the prime factors, you can instantly know a number's ultimate fate. How cool is that? All right, we've made it to the final stretch. Section 6, the Real Numbers Playbook, your board exam blueprint. Let's pull all of this theory together into a master playbook for Class 10 exam prep. To absolutely conquer this chapter, these are the critical target areas you have got to master. You need to confidently find the highest common factor using Euclid's division algorithm, remembering that whole step-by-step A equals BQ plus R process, and find the lowest common multiple using our prime factorization trees. You must be able to verify that magical relationship where HCF times LCM perfectly equals the product of the 2 original numbers. You need to use our prime DNA cheat code to spot terminating versus recurring decimals in a snap. You absolutely must be able to walk through that detective's proof by contradiction to show root 2 or root 3 is irrational. And finally, you need to easily express numbers in their standard prime factor form. Stepping back to look at the big picture, here is the complete evolutionary flow of the number system that you've just mastered. It's like a set of nesting dolls. We started as kids with simple natural counting numbers. Then we evolved and added 0 to get whole numbers. We went backwards into the negatives to discover integers. We learned about fractions and irrational numbers, and then finally we collided with those messy, infinite irrational numbers. Combined all together, they formed the complete, beautifully infinite, and incredibly dense universe of the real numbers. Ultimately, all these formulas, these division algorithms, these prime factor trees, they all point us toward a much deeper truth about our world. The number line isn't just a bunch of random digits on a page. It's a glowing, logical framework for reality itself. As this quote perfectly summarizes, mathematics is not about numbers. It's about understanding patterns and logic. When you understand the unique prime DNA of a number or the physical rules of how irrationals combine, you're literally learning how to decode the universe. Which leaves us to wonder, what other hidden patterns exist in the universe around us, just waiting for the right logic to reveal them?
Keep exploring, and I'll catch you in the next explainer.